The third paper of Einstein's about the photon was the only paper, the only idea that Einstein ever described himself as revolutionary. The paper was called "On a Heuristic Point of View Concerning the Production and Transformation of Light." What does this even mean, a heuristic? Well, it's come to be more frequently used in the world, but back then hardly anyone used it in science. It was the idea that sometimes a concept should be introduced that would so advance us in our understanding of the order of nature that even though it was only a provisional move forward, it wasn't a foundational idea, it wasn't a theory in the full sense of theory, it was really a gambit that if you took this seriously enough to reason from it, you could understand all sorts of phenomena that otherwise had remained mysterious, even though it was incompatible with other ideas that were well accepted. Einstein, early in the paper, says, "There exists a profound formal difference between the theoretical conceptions physicists have formed about gases and other ponderable bodies, and Maxwell's theory of electromagnetic processes in so-called empty space. Particles in statistical mechanics, the study of gases, for instance, could be counted. They're big numbers, like 10 to the 23rd of them in a reasonable volume, but you can count them. They have individual locations and velocities, even if we only approximate them in trying to understand the world around us. And then there's electrodynamics, electric and magnetic fields, for example. Those can't be counted. Those are continuous. And you could imagine, say, a flash going off, and the flash is a thinning and thinning sphere of light as it goes out deep into the cosmos. There's no limit to how diffuse or weak that electromagnetic field could be. It doesn't break down into something grainy. It's continuous. And Einstein, again, begins with a clash, an asymmetry. Maxwell versus Boltzmann, if you want to put names on it. Continuum versus the discretum. It's again like the conductor and the magnet looked at from two different ways. We're saying thermodynamics is continuous and Boltzmann is discrete. So Einstein then introduces a move forward, this time a heuristic rather than a rigorous theoretical postulate. The idea that light is also to be understood as undivided energy quanta, traveling in space, absorbed and produced only as a whole. You only get to absorb a photon or emit a photon, and the photon flies through space. You don't actually get to have half a photon. With this idea, he can explain all sorts of things. He can explain, for instance, Stokes' rule, that if you shine a beam of one frequency of light, one color of light, at a substance that's photoluminesces, the photoluminescence will always be of a lower frequency than the incoming light. Well, why is that? Well, Einstein says it's very simple. Each photon carries a certain amount of energy proportional to its frequency, to its color, basically. And that photon has a certain amount of energy, so when it does something in the substance, and that substance re-emits light, it can never emit more light than it absorbed. So it's always going to be of lower energy and therefore lower frequency. So it emits a lower frequency photon than the one it absorbed. Otherwise, it would be a magic energy producing machine that would be giving you more energy than it got. Can't have that, Einstein says. Another very important effect that Einstein predicts, which had mystified people, is the photoelectric effect. If you have a piece of metal and you shine certain ultraviolet light on it, you can get electrons to pop off its surface. And above a certain frequency, you could get electrons popping off very easily. But below a certain frequency, no matter how intense you made the beam, no electrons popped off. This mystified people. How could this be? It seemed like if you had a low frequency beam, but you made it intense enough, bright enough, you should be able to get electrons to pop off. But Einstein said, no, we can understand this by imagining that the light is coming in as individual photons. Imagine, for instance, This is not Einstein's analogy, but you have a garbage can with some tennis balls at the bottom, and you're throwing ping pong balls in to try to get them out. Well, until you have enough energy to actually raise one of the tennis balls out of the garbage can, it doesn't matter how many of them you're throwing in. If one's hitting the tennis ball at a time, it's never going to come out. It just doesn't have enough energy. But above a certain energy, when the photon, so to speak, the ping pong ball analogous photon, has enough energy, well then, as you increase the number of ping pong balls going in at high energy, then you're popping the tennis balls out right and left. This was a prediction that got the attention of the Nobel Prize Committee, and eventually, perhaps fearful of actually awarding it in relativity or for Einstein's many other contributions in cosmology, general relativity, they chose that because it was so startling. When Einstein's ideas were finally understood about the photon of light, that was something the Nobel Prize Committee could really put their hands on. But the objections to the photon theory came furiously. People said, how could light be both a wave and a particle? The wave theory of light was one of the best accepted triumphs of 19th century physics. And now Einstein was saying, it's not a wave, it's particle-like? That seemed crazy. All of the phenomena of the wave-like nature of light were just everywhere. If you buy some slides to use in experiments, for instance, they'll say anti-Newton on the top. And what they mean is not that they're opposed to Isaac Newton, but Newton had shown how you could have rings that you could see if two pieces of glass were close together. And certain glass slides are made to try to avoid those. And those rings are understandable easily in terms of waves. Or if you have oil on a puddle and you spread it out and the color changes, you're seeing the wave-like nature of light. Max von Laue said, it is only when radiation is exchanging energy with matter that it behaves as if it consisted of finite quanta. He was very hesitant to say that actually the quanta of light were sailing through space. And Henri Poincaré, as we've seen before in an earlier lecture, said that this was a contradiction, the idea that light could be both a wave and a particle. And from a contradiction, everything follows. In fact, it leads to a kind of destruction of science as a reasonable, coherent enterprise. So if we put these together, these three papers, each of which begins with some contradiction or asymmetry, each of which postulates something new as a way forward, each of which leads to experimental consequences, we can arrange the papers in a kind of wedge into the 20th century. The light particle, which Einstein gets to by thinking about fluctuations, modeled on the way you think about fluctuations in a gas or in a liquid, held together the light particle argument and the Brownian motion argument. In both cases, fluctuations are crucial. At the same time, the idea of light as a particle also gave force to Einstein's faith that you could get rid of the ether. Because if light was also particulate, and that somehow that particulate nature of light added up in a way he had no idea how to do, but if it added up to waves, then the idea of a particle traveling through a void without the ether seemed quite intuitive, and maybe that could help put on a firmer, understandable basis Einstein's disposing of the idea that you needed an ether to talk about light waves. So special relativity and the light particle were joined together through the propagation of light and not needing the ether. The light particle and Brownian motion were joined together by reasoning about fluctuations. And so you have a kind of wedge. The light particle at the intersection of his concerns in special relativity and Brownian motion, and the light particle leads eventually to reasoning about the quantum and eventually to the whole quantum revolution that will so dominate Einstein's concerns and everyone else's deep into the 21st century. So there you have it. Einstein does have a style. He has a way of thinking that's very different from most physicists, and it both entranced the public, it entranced his scientific colleagues, and it made him almost incomprehensible and sometimes repellent to some of his scientific contemporaries. Einstein had developed a way of thinking in physics that was startling and immensely productive.